Our first speaker is Chris Buggenhout from Dell. Chris has been with Dell for quite a while. He's an advisory system engineer. I don't quite know what that means. And he'll be talking to us today about some work that Dell have been doing with the University of Cambridge on the balance between power consumption and performance. Chris.
Thank you. So I'm just going to advance the slide a little bit. It's about seeking the balance between performance and actually power consumption. It's basically a case study that we've done together with the guys from Cambridge and with our engineers in the lab, seeing how we can, let's say, find a way to reduce power but still keep performance running with a specific application. Actually, a number of applications have been used, and these are basically GPU-based applications because that allowed us to do some of the trickery that we needed to do to actually go further. It was actually in the setting, in the scene of the Green 500, so that's the top 500 systems which actually consume the most, not consume less energy, but are the most energy efficient. Means that they are on the balance between using power and runtime, etc. That is actually the job gets done within the right time frame without using too much power. We use it during runtime, so well, the longer the application will run, the more power you will use, even though you're using less power. So there's that, let's say, flexing point that we need to find. So basically, it's based on the system Wilkes-Tree. It's a GPU-based cluster. We isolated a single rack of it with nodes to do our testing and have specialized metered, let's say, metered PDUs so that we can measure it. This is all being captured into a Grafana database, so we actually could see exactly combine this with the application runtimes. I'm going to go quickly because I have too many slides for my talk, so I'm going to go quick. Hold me back if you want to have some more explanations. So benchmark methodology is simple: run, change frequency, repeat. And it's on the entire rack for each. There's actually an application, NVIDIA SMI, which controls the GPUs, where we can actually change some parameters. One of them is limit the power, but that's brutal force limiting the power. But there's also a way of, let's say, lowering the frequency and setting to a fixed frequency. Means that the GPU cannot go beyond that clock frequency, and it will lower the internal voltages, so it actually is going to consume less power. But of course, performance will go down. So, yeah, I've already said this. Good. So it will automatically, and it's in steps of 50 megahertz. So that's a kind of fine-grained way of doing it. So, and if we then just plot it and use a HPL, which is basically the test we use for the Green 500, is that we plot the whole set about this, and then you see that this is the normalized, no changes to the frequency. And when we start dropping the frequencies, you'll see that the power goes down, and the performance actually is okay until here. So it's actually the performance per energy unit that you're still getting a good value. Once it goes back up, you'll actually losing it because of your runtime is going to into extremes basically. So one of the examples is, well, we've done this exercise is looking at really where's that flex point for a specific application. With HPL, this was the curve that we found at the bottom where you see, well, that's the flex point where it starts to go up again because of the runtime becomes longer. It's also tuning HPL is also a bit of a trickery because you can also change the values of your problem size to make sure that you're not running too big of a problem, because that's going to give you small percentages in performance increase while increasing your runtime dramatically. That means your power consumption energy consumption in total goes up, way up. So that's also, let's say, something you need to take into consideration. Other applications have a defined runtime on the problem side. So that's a different kind of approach. So we also did a lot of work, and that took a lot of time to run different kind of applications, finding different flex points, actually seeing that some of them actually can drop quite well, but then also quite quickly go into a, let's say, the throughput becomes a problem because your runtime becomes too high in the whole system. And there's all this is poultry tree, tea leaf, clover leaf, and then there's a weather code. We actually, it was really interesting to see that actually got some interesting results. And so milk is also one of those that has a very steep curve where it drops down in the power consumption, but doesn't lose too much in the runtime. So it's the plot time, that's the time to solution. That's also always interesting. So if you can keep that as short as possible while dropping the power consumption, that gives you a very valid, let's say, solution into the long term. Putting things into perspective, how we can do it. So this is just mapping how much increase in performance versus the decrease of solution time versus the decrease in power consumption. We always gain, let's say, quite a lot. So for HPL, we go 16% slower, but we gain almost 27% in power efficiency. That's actually very interesting to have. And in the long term, and especially in situations where your power consumption is a challenge, or you have a limitation to your data center, and especially if we're looking at the larger systems out there, they're running into megawatts or 10 megawatts or 100 megawatts, you start to see this becoming a real challenge. And if you have some of these applications which are running really to the maximum, and some of our, let's say, European countries that we get charged on the peak performance, peak power usage. So if you can actually keep that power at a certain level, as much as possible, then your runtime might be a little bit longer. In the end, you might be, but it's much more efficient. And in the TCO, in the end, you're actually much more better. So, and currently, with our Ukrainian situation, it's a bit of a challenge in Europe. So there's some additional things that we've been looking at. Maybe we can do limit the power with the iDirect, which is the BMC of the Dell systems. You can actually do this, but this will hurt performance because it's non-discriminatory. It will just do it and just limit the power usage. It's not allowing to throttle, etc., etc. The power usage itself for the NVIDIA already said this is also non-discriminatory. So it's going to limit the power it can use, but it's going to allow the boost of the clocks to a certain point. But it's going to limit it at a certain, and that's going to not, let's say, it's not going to be that interesting. The frequency was actually the more interesting path to choose. And controlling the memory clocks could be, for specific applications, a valid option, because that's also a power consuming element in the GPUs that we can actually reduce. And that's something that we might want to look at in a next generation. Forcing power states in clock frequencies is an option for the CPUs, but let's say, given transition times, that depends on your application and the usage. This is from a colleague of mine, Martin Hilgeman. I have to reference him because he's an amazing guy. He actually measured the impact of MPI on power usage. Because when an MPI wait state, it spins the CPU 100% cycles and consumes lots of power. But if you look at the let's say, it's very small to read on the slide, but the blue line is interesting. That's the Intel MPI. They found a trick to actually have the wait states in a lower CPU state so that the other cores that are not waiting, are actually calculating, get more time and get a higher frequency. So actually your time to solution shrinks, means your energy consumption in total has gone down, which is a very interesting one. And standard MPIs, well, OpenMPI, and it's actually not very good at that. It actually just keeps the CPU spinning at 100%, consuming maximum power, which is what you don't want. Slurm-based power management is also something that we've been looking at. Turning off nodes when not in use. Problem is, it takes time to power up, and it takes power to power up. And the time to boot up a system, it's about 5 to 10 minutes, depending on the size of memory. You will consume a lot of power during that stage of, let's say, self-post testing, etc. It's going to consume a lot of power. And you could do some hibernation tricks. We've tested it, but let's say the time to boot between a hibernated image and a cold boot is not that different, because the post is still the same. You're still going to do the testing of the memory. tools that can be used to control power, to keep that flat line on your power. Something that we've been introducing into our BMCs is to use a system that can control the power being used by the system. And this can be with a software stack. It's called Open Managed Power Manager, I think. And it can be group-based, rack-based, node-based, that you can tell it you cannot exceed a certain level. So if you have, for instance, 12 kilowatts, but you're not going to be able to realistically use more than 10 kilowatts, you can set into the system, into the power manager, you're not allowed to go beyond 10 kilowatts. Manage the groups, and you can set priorities. Some groups will have high priority. They will always get all the power they need. But others, they might be pushed a bit down. They will not stop. They will keep working, but they might be going slower slightly. So for HPC, sometimes maybe an interesting path, but mostly for where we see that the applications that are being used are non-essential applications or databases, etc., that don't get impact that much. And then we see that that is really a very valid, let's say, solution to keep a power within a certain check. And especially in Europe, let's say a lot of customers are really looking into this, and they are, let's say, interested in this kind of control because they don't want to, let's say, pay that peak, because that peak is extremely expensive. Forcing power states in the cluster itself, yeah. We've done some experiments. There's not that much improvement on the power usage itself. It all depends on the application itself. You could look at the application profile. If you do a good profiling of the application, then you could say, well, it's an IO bound profile. I can clock down the CPUs because CPUs will just be waiting, basically. Same with memory bound applications. CPU cycles, they can be relaxed a little bit. So you can lower that frequency and you can control that a bit. And that will, with minimal impact on the solution, time to solution, will, let's say, run the application in the highest performance capable within that energy envelope. Alternative cooling methods. We've seen that actually has an impact on power consumption. So what does it gain us? Well, we have fans. If we use DLC, we can remove some of those or run them at idle, which is between 1 and 2 watts in comparison to 25 watts. So, but the DLC also uses power in the primary loop. So the loop that DLC, the closed loop that's cooling the CPUs and GPUs, will be using power itself for the pumps, etc. So there's actually some trade-off here. You need enough systems to be connected to your DLC loop to be able to make sure that it works. And something, just a marketing slide that I had to include from my team. So we've done a lot of work on, let's say, making sure that our machines use less and less energy in total and are more efficient. And one of the tricks that we're trying to do is keep the fans as low as possible without getting the CPU throttling. That's where the DLC option actually comes into interesting, let's say, a solution, because that's keeping your performance quite stable. That's an observation we've done with the guys from Cambridge as well. All the DLC units, they have a very stable, let's say, predictable performance. And that brings me to the end.
Thank you, Chris. So are there any questions at the back?
Thanks for the talk. It's like sitting in a design review on our engineering meeting, because all the issues you covered here are the things we're trying to talk about. So, one of the things I'm looking at, and particularly in the South African context, is managing a site-wide power target. So this needs to include the site facilities, yes, cooling as well. Whereas the systems you're talking about here is really just focusing on IT.
Let's say system, let's say on the compute side, but let's say on the site-wide, you can, one of the things that with the power management suite that we do, we can actually input data from outside and get triggers or policies put into the system that actually then takes into account the whole package, because your chillers in the back end, your facility pumps are running. There's other things around the ecosystem of your infrastructure which are going to consume power, and that's often not looked at. But
yeah, 100%. And in the South African context, we have load shedding.
Yeah.
We've got renewable energies, which have variable inputs. So
Yeah.
it's becoming quite a big challenge to solve.
Correct.
How do you run the entire system at the optimal level, not exceed your peaks?
So that's where we are trying to find a way of doing that, and extending that power management suite to make sure that can get inputs from various inputs like green energy. When there's solar power, you can do whatever.
Yeah.
Just run free, or you can even define times where the system can consume whatever it needs. But there's times where I said, well, in a certain period of the evening when people are starting cooking, getting home, you squeeze the power down.
Yeah. Great. Thanks. I forgot to introduce myself. I'm Jeremy Main from the South African Radio Astronomy Observatory. So we're looking at the Status Center for the SK1 Mid-Frequency Radio Telescope in Cape Town.
Might be interesting to have a little
absolutely.
chat about it.
Thanks very much.
Any other questions? Oh, there's one there.
Hi, yes, I'm interested in your comments about profiling applications, and then depending on whether they're memory or CPU bound, tuning the system to be power efficient. Is this application profiling something your system would do, or is that an input you take from somewhere else?
It can be input taken from somebody else, but we're trying to make our own profiles as well. But of course, there's always these customers that have their own homegrown application. Then they need to do the profiling themselves. And then that profile can define what can be done. But that's a conversation with engineers that we mostly, let's say, kind of a consultant-based engineering conversation that we do, which is in most cases basically an HPC.
Okay.
Ask the same question after the presentation.
Yeah.
Any further questions? Anything online? Okay. With that, then I'd like to say. Thank you very much, Chris, for your contribution.
Thank you.
And thank you.